My name is Michael Getz. I am also at IUB in James' lab. Today I will be going over chemotaxis, which will be a natural continuation of what Gilberto just taught with with adding a vector force. As always, you can find the slide decks on the Google Drive. You can download the exercises along with the slide deck itself. Uh, and we want to remind you of our funding sources. So today we will be going over generally how cell movement and gradients exist, chemotaxis itself, do a simple chemotaxis model, show how chemotaxis exists in CompuCell3D and how to specify it. Then we will be doing a constant gradient example, a logarithmic gradient example, and a self-constructed gradient example. Due to time, that's where we end it, but in these slides, there's also extra content of issues in understanding chemotaxis in CompuCell. And then two, you can consider it homework. We're not going to collect it and grade it later, but looking at chemotaxis dependence on parameters in a more complete way, and then a macrophage chasing bacterium example.
We're going to do some of those exercises this afternoon in 4.3.
So cells, of course, respond to their microenvironment through movement, and there's many ways that they do respond to their microenvironment through either gradients or temporal variations in their environment. This cell movement is, of course, extremely significant to how the cells respond and how the cells react to their microenvironment, and they can exist in various forms, such as durotaxis, haptotaxis, galvanotaxis. And what basically is happening in each of these is either substrate rigidity, so looking at the rigidity of, say, the ECM, looking at the substrate and finding a gradient in the rigidity, which would be haptotaxis, looking at electrical field or temperature variation, right? The cell's going to move away from an area that it doesn't like. But today we will be going over chemical solute gradients, aka chemotaxis, and showing how to encode that into CompuCell. So I have two, well, it's really just one example, but one informs the other. So chemotaxis is just finding gradients in the microenvironment. So in this first video, you'll see a pipette dropping some cyclic AMP, and then you can see the dictocilium moving towards the pipette tip in response to the signal gradient. Now, if you look at it in a larger scale across some amoeba that will provide the source of cyclic AMP in a pulsing sense, you can get really cool behaviors, such as this large-scale spiral wave patterning that I think the video broke. Which allows for these really cool types of gradients due to the cell movement within itself and their involvement with the microenvironment. If I let this go long enough, you'll see that there's a resultant pattern of within the environment. So another example that I like to show is a white blood cell chasing a bacteria through a complex environment. So you can see the bacteria here, and the cell will constantly track it due to the hormones that the bacteria is giving in the microenvironment. So this is exactly how the immune system can help determine what cells may need to be engulfed. So how exactly we model chemotaxis in CompuCell is we use, similar to in the previous section, an instantaneous dissipative force, which we say is proportional to the energy contribution to the to the Hamiltonian, which is just the energy field within itself. So what you have is two components in this example. There's some gradient of concentration between your source and pixel cell, your lambda chemo, which is very similar to the lambdas seen in the previous sections. It just tells you the strength that this energy contributes to the total energy functional. And those together, you can start to cause forces. But you can, of course, with misuse, you can have interesting ideas that we will kind of go forward. One, the cell will move infinitely fast if you give it a constant acceleration through this force. The cell movement will not cause advection because, at least by default, so the cell will not push the signal itself. And without telling the cell to, the cell will not remove the chemical from the environment. They are just sensing the environment. So I want to get in the weeds a little bit. And this is kind of exactly how CompuCell does this flip attempt and applies this force. So by default, CompuCell will use the agent-focused algorithm. And if we consider our system has a energy contribution, which is just linearly related to the difference in the source and target cell, then we can see the contributions, of course, will be if I have cell 1 trying to flip cell 2, it will just be 10 times grad C. The thing I want to kind of make a point of with CompuCell's default sampling algorithm is that the lambda will inherit the source in all cases unless that source pixel has a 0 lambda itself. So the easiest example would be this middle one right here, where a medium cell denoted by the white is trying to flip the target cell of cell 2. And you can see if it was only forward, you would have a 0 energy contribution because the medium doesn't have a lambda chemo. But with the agent-focused default, because that lambda source is 0, you inherit the target lambda. And what you basically need to understand at a high level is that this allows for retraction events in the case that it's not two cells actively generating a force. What I want to pose to everybody is if we take this cell inside this field, which has the concentrations given by the value in the field, which direction will this cell be more likely to move in? If we use a linear gradient with some lambda chemo, we don't need to worry about the exact value of that lambda chemo. So south, not quite right. Bottom right. So you see a couple of those in the chat. So you can see, bringing up what I brought before, you will get retraction events due to the algorithm sensing, but you're more likely to have down acceptance and right acceptance. So you would end up in the bottom right. Oh, so each copy just responds to what is the energy contribution with each of these pixel copy attempts. Just saying that each of these attempts has their own delta H contribution because it's between a target and a source pixel explicitly. So you can define these through the XML level. And there's a number of options that you can put. Namely, you can say what you can chemotrack towards, what the lambda value is, and what cell allows it. So in this case, you have a cell A and a cell B. Cell A can only chemotrack towards cell B, What this means is cell A will only get the energy contribution when it's trying to move into cell B. In other words, if cell A is trying to move into your medium space, which is your, there's no cell present, it will not, T and S are target and source. So it's the pixel that you're attempting to copy into the next pixel. So in this example, cell A will only chemoattract towards cell B in that it only gets the energy contribution into this a pixel if it is of cell B. So we will go and do our first, well, first remind you some of these options. So you can find the XML option in CC3DM, L plugins, Chemotaxis, and it will generate a sample block for you. You can also edit Chemotaxis at the Python level by doing CC3D Python Chemotaxis by cell ID. When you originally create it, you want to use define. If it's already created, you generally want to use modify. You can technically get away with always using define, but it's generally better to use modify when it already exists. So you can also generate plots with, of course, CC3D Python scientific plots setup start function, which you want to create this in the start function as we have gone over in previous sections. It depends on which one you want to use between XML and Python for your use case. Python will let you edit it during runtime, as in between MCS. If you want the Lambda chemo to change in response to something in the microenvironment, you should use Python. If it's going to be constant the whole time, you are perfectly okay just keeping it defined in the XML level. So for the first exercise, we will go through and create a constant gradient with a single cell and chemotaxis. So I will walk you through creating this in Wizard myself. Although I already have it created, it's probably easier if I just show it, right? So we can do CC3 project, new project, give it some name. So I will just say E1. Pick some directory. It does not, the only thing that matters there is that the directory is writable. And then we will be doing lattice dimension of 200, 100, and Z of 1, because we are doing a 2D simulation. We want our cell lattice to be periodic in both. And I'll leave the images for anyone who falls behind so you can see them. They are on the slide itself. And then we do a rectangular slab for the initial addition. We want to create some cell, which we will fittingly call cell. Make sure to add it to the table. Then we want to make a field, which we will call oxygen. Make sure, and using diffusion solver FE, we want to add that to this field. And then for behaviors, we want to select contact, volume flex, and chemotaxis. Which will then bring you to this plugin window, which I will go over here in a second. In the next slide, we will be going over the Chemotaxis plugin window itself to help you define that value. So when you get to the Chemotaxis window, we will be defining a few value. we will be defining what the lambda chemotaxis will be in field 1. Enable chemotaxis toward medium itself, which you can either type in field 2, or you can hit the chemotaxis towards button with cell type medium selected in the dropdown, and it will autofill that. And then you want the chemotaxis type to be regular. What this is the functional. So regular is just a linear difference between the two values. And then we want to add entry, so it will create this box. You want that box to match what I have in this image. So wait a little bit to let everybody make sure that they have this plugin window, the wizard window filled out. So I will be, can I explain the difference between regular saturation and saturation linear? I will describe those briefly in a bit, but for now, just use regular. And what regular is it's a linear difference. What these do is they set the functional form that you're giving for the energy difference. We will go to the next. So now we need to start to define certain properties in the XML itself. So in the XML file, we want to create a constant gradient using the initial and boundary conditions. So the suggested way to do it is you want to set your diffusion constant to 0, your decay to 0, and then provide it with an initial concentration expression that will go between 1 and 0. Then you want to make sure your boundary conditions will match. So at x min, you want it to be 1. At x max, you want it to be 0. And then y can be periodic. A big note to make, by default, it will create cell-specific and secretion fields and assign it values in the XML block. You do not want those to function, so make sure you remove those. What we want is just a field with 0 decay, 0 diffusion that linearly decreases from 1 to 0 across the whole field. A big reason why it's divided by 200 in this is simply because the simulation domain is 200 within itself. So this is what my diffusion solver FE block looks like. You can see the plane axis for x is constant value 1 and 0 for min and max, and just a constant derivative of 0, 0 in the y-axis. I'll check the time to make sure I'm moving. Okay. Diffusion coefficient, we want it to be 0 for our diffusion coefficient value. Oh, so do we not need to add periodic to y boundary? You can add periodic, or you can add no flux. Yes, the value we're changing is the global diffusion coefficient. And setting it to 0, you want no movement of the field. You want it to have all the fixed values that you have prescribed through all time. Yes, so we do not need to add periodic to y boundary. We either want to do periodic or no flux. Both will be functionally equivalent. Periodic, because we have no diffusion, is going to functionally act the same. Okay. After we've done that, we want to initialize the cell close to the right end of the domain. I will show you what my block looks like to do that. You're just using uniform initializer. and then create a width 10 cell that is close to the edge of the domain and right in the center of the domain. What would be cell type diffusion coefficient? Yes, you either want to comment it out or remove it entirely. You want to make sure it's there. Yes, that looks correct. Johanna, generating the field. Okay. So once your field is created, then you want to define a single cell that initializes itself close to the end of the right-hand domain. The right side of the domain, sorry. Any quick fixes checks for an entirely blue field? I would make sure that you have assigned an initial concentration expression. Or you want to check your config to make sure that it is not maxed, yes, as Ripa just commented, you want to make sure that the your config isn't set up to constrain the system. I will. To test run this, I need to leave this full screen. So then we can start to run a simulation. To really look at it closely, you will want to set up a plot window, which you can do defined by the snippets earlier. Yeah. So you can define through doing CC3D Python, scientific plots setup. You want to create this in the start function. It should, the field values and what you're assigning should do that. You are doing this in the Python level. Yes, Van, it seems like your cell is secreting, so make sure your secretion value is 0. So now, so we can plot these values, we want to create a plot by doing add new plot window in the start function. For this, I gave it a title, position, time. You can technically leave these empty. The big thing is you want to make sure these exist. And then in the step function, you loop over your cell list, and then you add data point position with the X value of your MCS, which is your time, and then your cell center of mass. So it's hiding itself. Okay. And then when you run this, you should get something similar to here. You see your cell in the right-hand side, and it will slowly try to move across the domain while tracking its center of mass. Yes, let me go back to here. I will keep it on this field. So this is how you generate the plot on the right-hand side. Thank you. Sorry. So once you've completed, you can then go and modify the XML itself. So I added a 0, made it 10 times larger, and you can see as before, you're adding a higher energy potential to the movement, and therefore the cell moves a lot faster through the domain. There's a point to make, similar to the last module, that at a certain point, the cell will start to tear itself apart because of this energy, or it will hit its speed limit. So this still, of course, exists in chemotaxis because functionally you're doing the same operation as before. It's just now what applies this energy potential to the movement is dependent on the concentration field itself. Right? So now we can start to ask questions on what does this linear function mean? So if we wanted to say change it from a constant to a logarithmic field, logarithmic gradient, you can very easily see where a linear difference starts to go wrong. The cell will infinitely start to increase in speed until it hits its speed limit or it tears itself apart. So this is why there are other options outside of regular itself to allow the energy to either downtune in very high energy, very high gradients, or increase in very low gradients to allow the cell to sense the field more effectively. Ripla, if you have two cells, then likely you need to look at your uniform initializer definition. So you want to make sure that the width is equal to the size difference between boxmin boxmax. So in this case, I did 10, and you can see the difference between x and y is 10. So now we can start to ask different types of strategies that we can sense this gradient with. So one way to look at for a logarithmic field is to, and very quickly, what did you change to have it move faster? Your lambda chemo. So it is the value in your chemotaxis, your lambda. So now we can start to ask, what are the other types of factors we can do? So one is one of the other options that you guys would have seen at the start, logarithmic chemotaxis. What logarithmic chemotaxis does is instead of just taking the linear difference between the target and source cell, it applies a coefficient that takes your lambda chemo, which is similar to what you defined earlier, and then defines it by some value S, which you can define, and then adds the concentration of the cell center of mass before the flip attempt. So what this does is it allows it to dampen the effects of high concentration while trying to retain the differences, while we're trying to retain the gradient strength. So it takes your gradient strength relative to your concentration at your center of mass, added by some factor S, which is your log coefficient. What the S does is it allows that very low S center of mass, it will only consider the gradient, similar to something like a Michaelis-Menten function or a Hill function. So we can still use the same simulation, and then generate an exponential gradient by, you could do it by setting global decay coefficient to 0.1. What I would recommend is what you can exactly do is you can just modify your XML and set your initial concentration expression to this, which is just E negative root 0.001 divided by 0.1 over X. And what this will do is it'll give you a logarithmic decay across your field. So what you can check first is change this, and then without updating the chemotaxis, see how it runs. Likely you'll find that the cell will either not move much or will move and then continue increasing movement, similar to this plot given here. Oh, this plot here. So it will slowly increase until it hits this logarithmic portion and then increase exponentially until it hits the end, or it rips itself in two. So there are a couple ways that you can define these values of S and lambda chemo. One way is through the wizard. The other is through a Python definition. I will not be going over how to do this, but I wanted to include this here so you are aware. You can set your log scale coefficient at the Python level also. If you do set your log scale coefficient at the Python, it will know to use the log scale formula. If you want to apply it in XML, it is as simple as just adding log scale coefficient to the chemotaxis by type value itself. You can do it at start, or you can do it in step. So step would allow you to change it at any MCS. So if you wanted lambda chemo to be variable for some reason, at start, it will just set the lambda chemo at start, and it will inherit through all MCS. So yes, at start works if you are fixing it. You can also modify it in the XML. I have highlighted the the tag that you need to add to your chemotaxis block, or you can have Wizard generate this itself. So once this is complete, you can then run it with the log scale coefficient. You'll see a few types of behavior, which I'll generally ask why you think this occurs. This is dependent on both your lambda chemo and your saturation coefficient, where if you have a lambda dominated system where it's only dependent on lambda, it will create this linear. But if you have some variability, you will get this slow decrease into increasing decrease of the value itself. Yes. One, if you want to leave to Dr. Zhang's talk, it has started. I will not feel offended. And two, I have changed the lambda and log scale coefficient. I've done this just to allow a value. So I will show you the result itself. This allows that these values here will give you the first response where you have a slow, so initial movement, and then it increases as it goes. Once it hits the, yeah, you can see it speeding up. Once it gets into the stronger gradient area and it starts to outpace its saturation coefficient, or this one's linear. No, this one slightly moves down. Okay. So by playing with these values, both log scale coefficient and your lambda, you can get generally two types of responses shown here, where you get this very fast increase as before, or where the log scale is dominant, it will just give you a linear, which tells you that it's moving at a constant field, at constant speed. If you think that your graph is kind of moving up and down too much, likely what you need to do is allow for more MCSs to occur because of the stochastic nature of cellular PROTS itself. You can expect noise, which will smooth out along longer timescales. So what the energy contribution does is gives a trend to moving towards an area, especially at lower contributions. But the cell can have probabilities that can cause it to move back slightly. So as long as the noise is, so the value of log scale coefficient is 0.1. So as long as the noise is small, at least within half a pixel to a pixel, then you are perfectly okay. And I would not spend too much time worrying about that. These values that I've given here aren't set in stone. These are just values that I picked myself. I would encourage everybody to play around with these values and try to generate a intuition in how log scale coefficient and lambda affect the system within itself. So I will skip this because James, you said you were covering this in the later session.
Pedro's going to do it, yeah.
Pedro's covering in the later session, so I
Wouldn't
will...
hurt for you to explain the problem, but we'll do the exercise in the later session.
So the S value in the code is your log scale coefficient. So if I go back to the definition, this is the S value in the code. What it tells you is what you're defining the lambda chemo by added by the concentration at the center of mass. This will be the last example of this module. But in the later session, you will be looking at chemotaxis in response to self-generated gradients, where a cell within itself will secrete a nutrient, will consume a nutrient while moving through the area, and this causes the cell to move by itself. So it will end up creating little trails that it ends up eating the initial substrate. The S value in the code is your log scale coefficient. What this means is it's just the value that lambda chemo is getting divided by, added by the concentration at the center of the mass. So just some value that makes the system act linearly at low concentrations, but as you get to higher concentrations, you end up with delta concentration over concentration center of mass. So it starts to act in a more logarithmic function, in a more logarithmic behavior at high center of masses, much greater than S. But when S is much greater than center of mass, you return the linear formulation. I will hold this screen up. If anybody has any questions or wants me to show a different portion of the XML that they fell behind in, please feel to ask a question.